Welcome to this explainer. Today, we're acting as data detectives to crack the code on a key Grade 7 review and transfer lesson, Statistics and Probability. Specifically, we're diving into Supplemental Statistics Unit 8, Lesson 1. Whether you're making sense of tables and graphs, reviewing statistical quantities, or just trying to predict the outcome of a game, these tools are literally your secret weapons for making sense of the world around you. Let's get right into it.
Here's a quick look at our roadmap for today. We'll start with making claims with data, move into populations, samples, and bias, check out understanding probability models, run through the tile experiment, and finally wrap things up with a test your knowledge section. All right, let's jump straight into section 1, making claims with data.
Now, the core idea here is that you can't just make a wild claim about the world without solid data backing it up. We see claims everywhere, right? On social media, in ads, on the news. But the absolute bedrock of a good statistical claim isn't just the final numbers or the fancy graphs you see at the end. It completely depends on how you collected that data in the first place. To get this right, we have a few key goals for this lesson. We're going to use random samples to make claims, compare data distributions, calculate some simple probabilities, figure out the difference between theoretical and experimental probability, and organize compound events. Master these, and honestly, you master data. Moving right along to section 2, populations, samples, and bias. This is where we build our data vocabulary. First up, the population. And hey, in statistics, this doesn't just mean the number of people living in a city. Whether you're studying all the 7th graders in your district, every single registered voter, or literally every pine tree in a forest, the population is the complete, exhaustive group you're investigating. It is the everyone or everything of your specific question. But here's the catch, right? We almost never have the time or the budget to survey the entire population. It's just not practical. So we use a random sample. This is a smaller, randomly chosen subset where every single member had an absolutely equal chance of being picked. We use this smaller group to uncover truths about the whole shebang without ever having to ask every single person. Which brings us to the bad guy of our story, bias. Bias is the ultimate enemy of a good data detective. It's a systematic error that happens when your sample goes wrong. If your method of picking that smaller group is flawed, your sample no longer accurately represents the whole population. And your results, well, they're completely skewed. So data collection is truly everything. A random sample is fairly chosen, it accurately reflects the population, and it leads to valid claims. A biased sample, on the other hand, is unfairly chosen, completely misrepresents the population, and leads straight to false claims. If you build your statistical house on a biased foundation, it's going to collapse, for sure. Okay, let's shift gears a bit for section 3. Understanding probability models. We're moving from collecting data to predicting the future. At its core, probability just describes how likely an event is to happen, and it exists entirely on a neat little mathematical scale from 0 to 1. 0 means an event is completely impossible. No way it happens. A 1 means it's absolutely certain. Everything else, every dice roll, every weather forecast, lives somewhere in between those two numbers. Now here is where we see the classic battle between expectation and reality. On one side, we have theoretical probability. This is what the math predicts should happen in a perfect, flawless world. On the other side is experimental probability, and that's the messy reality of what actually happens when you run the test yourself. And this brings us to a huge misconception alert for this unit. It's super easy to fall into the trap of thinking theoretical math guarantees your short-term outcomes. If you flip a coin twice, math says you should get one head and one tail. But in reality, you might easily get 2 heads. Probability doesn't predict exact short-run results, it predicts long-run patterns. The more you test, the closer your messy reality gets to the perfect math. Let's ground these abstract ideas with a worked model right out of the lesson in section 4, the tile experiment. Just imagine you've got a completely opaque bag. Inside that bag, you place exactly 10 tiles. 3 of them are red, and 7 of them are blue. If we want to find the theoretical probability of reaching in and randomly pulling out a red tile, we just look at the numbers. 3 out of the 10 total tiles are red, so the probability is 3/10, which converts perfectly to 30%. The math tells us we have a 30% chance on any given pull. Tying this right back to our misconception alert, if you repeat this experiment 100 times, putting the tile back after each pull, you'd expect to see a red tile about 30 times. But getting exactly 30, that is not guaranteed at all. You might get 28, or maybe 33, because of that short-run variability. Over thousands of polls, though, you'll zero right in on 30%. All right, we've covered a ton of ground today. It's time to pause, think, and jump into our leveled practice for Section 5. Test your knowledge. Let's kick off this check for understanding. Imagine you want to know the favorite lunch food of your entire middle school. Why is surveying only your closest friends at your lunch table likely to give you biased data? Think back to our vocabulary for a second. Well, the sample may not represent the whole population. Your closest friends probably share your interests, maybe even your exact taste in food. Because of this, they are definitely not a random sample, and any claim you make based on their answers is going to be heavily biased. Okay, let's try calculating a simple probability. You have a board game spinner divided into 8 perfectly equal sections, and 2 of those sections are colored green. What is the probability of landing on green on a single spin? We just follow the steps for flexible representations here. First, we write the fraction of our target outcome over the total outcomes, so that's 2 over 8. Step 2, we simplify that down to 1/4. And step 3, we convert that to our final probability, which is a solid 25%. Last question. Let's connect our probability scale back to a real-world expectation. If an event has a theoretical probability of 0.75, how many times would you realistically expect that event to happen if you ran exactly 100 trials? You'd expect it to happen about 75 times. You just multiply the probability by the number of trials. But remember, we say about 75 times because of experimental variance. So, as we wrap up this explainer, I'll leave you with this. The next time a politician, an advertiser, or an influencer makes a bold claim on your feed, will you take it at face value, or will you use your new data detective skills to question the numbers behind it?